Okay, so let's finish our discussion in this lecture of chapter 15, our lecture on submerged bodies. And where I left you last time is with the question of why can deep sea creatures survive at great depths? Survive at great depths. After all, it hurts our ears when we dive down to 10 feet below water. How is it that they can survive at great depths without being crushed? Last time we talked about compressible bodies underwater, and that's what's being shown in figure 14.1. So let's directly now answer this question. Why is it that deep sea creatures survive at great depths? And here is the answer that Pascal provides. He says, he first of all notes that pain is caused not by pressure itself, it's caused not by pressure, but rather by deformation of tissue. By the deformation, that is by the shearing or the stretching or the tearing of your tissues. So in other words, if there is no deformation, if there is no deformation of your tissues, then there is no pain. Okay, so one feels pain at great depth, for example, on your ears. So the pain in your ears is due to the deformation of your tissue separating the outside from the inside of your ear. So on the outside of your ear, you have this very high pressure water, and on the inside of your ear, you have ordinary pressure air. And so what you have is this deformation of this tissue, and that is precisely what causes the pain, the stretching of that tissue. If, on the other hand, if the pressure was the same inside and outside of your head, then there would be no pain. So this goes back to this idea that the pain is caused by the deformation of this tissue. And this is the key to understanding how it is that these deep sea creatures survive at great depths. So if the entire body, if a creature's entire body is in equilibrium, that is the same pressure everywhere, pressure over the entire surface of the body, over the surface and the interior of the body, then there's no deformation and no pain. And no, I would even say no damage to the body. Okay? And this is precisely the point, is that sea creatures are in equilibrium with the ambient pressure. Pascal gives a few examples. So let's look at a couple of examples of these sorts of things to try to prove his point. So the first one he talks about is, let's suppose you take a worm and you put this worm into some dough, and then you compress this dough with your hands equally everywhere. So notice that as long as the dough is pressing equally everywhere on this worm, then what happens, there's no sort of shearing of the outside of the worm. And this is page 195, by the way. On page 195, the worm is uninjured. Now, I would imagine that if you did this really fast so that the interior of the worm was at a different pressure than the exterior, it might feel some pain. But as long as you press this down slowly and keep increasing the pressure more and more so that the interior of the worm has time to come into equilibrium with the exterior, I would imagine that this worm would survive. I guess that's one caveat I would add to what Pascal has been talking about. So this is the worm in dough scenario. I suppose you could try this at home and see what happens. I don't know how you would know if the worm is actually in pain or not, but I think wasn't there a book that Consider the Lobster that was talking about whether lobsters feel pain or not? Yeah, that was a very distressing essay. Okay. He wrote Infinite Jest also. I haven't read that. It's really long. Sounds good though. Okay, here is the next example that Pascal provides. He says, suppose that you have water in a cylinder and you put a fly in the water. So I'm going to draw a little fly in here. Apparently flies can survive underwater. Again, this is news to me. Those of you who are biologists maybe have tried something like this. I don't know. And then suppose you put a piston, let's make it this like a metal or a copper piston on the top, and you apply a pressure, a force to this, that is, you weigh it down. And what Pascal claims is that the fly submerged in water will just continue to walk around on the inside of this glass tube. As you apply more and more and more force, it will be just fine. It'll be walking around inside of here. And then if you release that force and you take the copper thing off and you drain the water, the fly will fly away. That's what Pascal claims. Again, if you want to try it, you're welcome to give it a shot. I haven't done that. Here's something that I have done though. This is kind of fun. So if you take an Erlenmeyer flask, draw an Erlenmeyer flask like this, with a port on the side of it and a port on the top of it, and you plug this Erlenmeyer flask with a cork after having filled it with water. So here's some water. And borrowing a goldfish from your friendly neighborhood naturalist or biology teacher. So I took a goldfish from Dr. Anderson. He said I could do it. And I put this goldfish in the water. And then I had a valve hooked up to this Erlenmeyer flask. And this I hooked up to a vacuum pump. And what happens is, this fish is swimming around in here. As you pump the air out of this, the pressure of the air drops and the pressure of the water drops. And so what happens is the goldfish, in order to keep swimming around, it has to basically get rid of the air in its swim bladder. So it's going to start burping up bubbles like this because it needs to maintain the same pressure inside and outside of itself. So it ejects this air out of its swim bladder in order to keep swimming around as you're pumping this air out. And so it's still swimming around, it's doing just fine. And this is the interesting part. Now, what you can do is you can, whoops, let me redo that. So you take this Erlenmeyer flask with the fish in it, and you close off this valve right here, so it's very low pressure inside of it. Let me draw the water once again. There's the water inside of this Erlenmeyer flask. And then what you do is you suddenly pop the cork off of the top, and what happens is all this air will suddenly rush back in, increasing the pressure, and what happens to the fish is suddenly the fish falls to the bottom of the Erlenmeyer flask and sits there and kind of wriggles around on the bottom of the Erlenmeyer flask because now it is no longer in equilibrium with the water around it. So it's kind of lying there on the bottom. And I was told that the fish doesn't feel any pain, so it's just kind of lying there on the bottom. And I felt kind of bad for him though. So what I did is I took him and I dumped him back into the aquarium with his friends, and he sunk down to the bottom of the aquarium, and his friends came over and were swimming around him and sort of, asking him apparently if he's okay, and he was sort of flopping around on the bottom of the tank. And over time, what happens, I watched him for a few minutes. I hoped he was okay. I left and I came back, and sure enough, he was up and swimming around. So apparently what happens is he's able to absorb air from the water around him to reinflate his swim bladder, and then he's just fine. So the fish was okay. No fish were damaged in that situation, but it's an interesting example of how animals equilibrate with the surroundings. As one warning, I guess you cannot do this with any kind of fish. The critical thing with the specific kind of fish that the goldfish is that its swim bladder is attached to its esophagus, apparently. So it's able to deflate its swim bladder through its throat. If they're separate and you try to do this, you could rupture the swim bladder and hurt the fish. So it's important you don't do this to just any kind of fish, but only fish that have their swim bladder attached to their esophagus. In any case, I will talk to you in the next lecture.